Breaking Bad, you've probably heard the name Heisenberg. But do you know who Heisenberg was? He was a German physicist and is one of the founders of quantum mechanics. You may have heard about Heisenberg Uncertainty Principle, which states that we cannot know the exact position and the momentum, which is really the velocity times the mass, right? We cannot know these two quantities exactly at the same time. And so we can only know them with an uncertainty who's above this amount. And we're used to thinking about this applying to a particle, right? Like a small particle, like an electron or a proton or something. But it's actually applying to everything. A ball, a plane, a human. So let's just do an example on this to find out. What we're going to find out here is that if we're assuming that we know the position of an electron to an accuracy of 1% of the hydrogen radius, we're going to calculate the uncertainty of the velocity of the electron and compare this value with the uncertainty in the velocity of a ball whose position is known to an accuracy of 1% of that radius. So that sounds kind of plausible, that we have the uncertainty is like 1% of the radius of the object we're looking at, right? And so all we need to do now is actually just plug in the numbers. And we know that the change in momentum equals the change in mass times velocity, right? And so we assume that we look away from relativistic effects and we say that the change in mass is zero. So we really have here that the change in P divided by m equals the change in the velocity, which we're going to find here. So we see that we have to divide this expression by m. So let's rearrange this. Okay, then we're ending up with really that the change in velocity equals the Planck's constant, and this is just simple algebra really, times 4 times pi times the mass of the object we're looking at times the change in x. So it's the uncertainty here in, or how precisely we know the position. And so the change in velocity for the electron is then the Planck's constant, the value of 6 times 10 to the minus divided by, that did not look good. Okay, so we're dividing it by 4 times 3.14, right, times the mass of the electron is 9.11 times 10 raised to minus 31. And we have to multiply this also by the change in x here, which is 5.10 raised to the minus 13. And so the answer that we get, I calculated this on beforehand, but you could do it yourself also if you want to, is this huge number here. It's almost like as fast as the speed of light. So we do not have a chance of assuming the speed or the change in momentum of the electron, really. All we can do is use probability functions. Now, let's do this by the ball. And so it's just really the same. But we just plug in the new numbers that we have for the ball, which is, for the mass, 0.2 times the uncertainty in position, which is 5.10 raised to the -4th. And the number we get here, you should actually try to plug this in. Just for fun, I recommend it. So it's really not to believe, but it's 5 times 10 raised to -31 meter per second. So you see that this is a very small number. So that's why we're saying that for these big objects, we're not thinking about this principle. But really, it does apply. It's just such a small deviation from what we actually measure. But when it comes to small particles in quantum mechanics, we see how important this is.